सो या ओके, थैंक्स फॉर कंफर्मिंग एवरीवन। आवाज़ आ रही है। सो जो ये वाला स्ट्रीम है जो भी कर रहे हैं, ये अनअकैडमी और यूट्यूब पे साइमल्टेनियसली किया जा रहा है। लेट मी जस्ट चेक कि यूट्यूब पे सही से स्ट्रीम हो रहा है। जस्ट गिव मी अ मोमेंट टू चेक। सो वी चेक टू चेक दैट। Yes, this is for div 2. So is it working on YouTube? Is it streaming? Just give me a moment to check. Just one moment, please. Yeah, okay. So I am there at YouTube as well. So it is fine there. Uh, okay, so you're saying that it's lagging a lot. Is it lagging on YouTube or Unacademy? Just give me a second to check my internet speed. Well, the speed is fine. I am not sure why is it lagging. Could you please try and refresh? Yeah, okay. So people are saying it is not lagging. All right. All right, great. So, so yeah, good evening, guys. I hope you are as excited for the camp as I am. Uh, my name is Pulkit Chhabra, and in this today's class, we'll be discussing introduction to trees. So let me just sort of give you an idea about what the content will be. And before that, let me just briefly introduce myself. So like I said, my name is Pulkit Chhabra, and I am a fourth year computer science student at Delhi Technological University. So, out of all the educators that are taking this camp, only me and Nishchay are the ones who are in the college. The rest all are working in uh, uh, companies like Google, Facebook, and so on and so forth. So, some people are saying that am I muted, but for others the audio is fine. So, if for those who cannot hear me, uh, please try refreshing. All right. Great. So you guys may know me as coder underscore Pulkit underscore C from CodeChef or Code Forces. This is the handle that I use. And yeah, if I'm to talk about my profiles in brief, I'm a master on Code Forces, and uh, I'm a 6 star on CodeChef. So yeah, let's just move on. And in this today's class, in this today's introduction to trees class, what I'll be doing is in a very brief manner, I'll be just explaining what a graph is, what a tree is. I'll try to take the least time there. Then we'll see what different types of trees are, different ways to represent trees. Having spent some time on introduction, and then we'll move on to some simple problem solving parts related to depth first search. And if time allows, we'll try to solve a couple of problems, one or two problems related to deep on trees. All right. So sounds good. Give me a thumbs up. Shall we continue? Great, great. Someone is saying that I look like Abhishek Company. Yes, I have heard that a lot. Okay, so just to give you an idea about the chat, I'll be looking towards the Unacademy chat very frequently. For YouTube, if you guys want to have a very good sort of interactive experience, I'd suggest you to come to Unacademy. But otherwise, if you just want to see the class and don't want to interact that much, then YouTube is fine. All right, so let's begin. B, since we don't have a lot of time, we have an hour. I'll try to be slow. I'll try to repeat things, but please be alert and listen to what I am saying very carefully. All right. So let's start with what a graph is, because trees is sort of a subset of graphs, right? So let's start with graphs. So a graph is a representation of set of objects where some objects are connected by links. For example, let's say we have some cities. We have the city A, we have the city B, and we have the city C and D, and so on and so forth. Let's say Delhi, Bombay, and so on and so forth. And there are some roads between them, which can be represented as links. Let's say there is a direct direct flight from A to B. Let's say there is a direct flight from C to D, and let's say there is another city E. There's a direct flight from B to E as well, and there is a direct flight between A and E as well. So this network of lights and cities can be represented as a graph, right? Now, now if you notice that this sort of subgraph here, which consists of the nodes, which consists of the cities C and D, has nothing to do with this subgraph. There is, what I mean to say is that there is no flight connecting any city from this component to any city from this component, right? So these different two components are called connected components of a graph. So if I talk about this particular graph that I have written here, it has two connected components. This is one connected component, and this is another connected component. So this has two connected components. All right. Now also, if you notice in this first connected component, if you notice this first connected component, there is a cycle. If you notice, if I start from a node A, if I start from a city A, what I can do is I can go to E, then go back to B, then come back to A. So this is what we call a cycle. All right. So I have defined cycle. I have defined what a connected component is. So any graph which has just one connected component, for example, I draw this, I've just drawn this graph which has two connected components, right? Let's say there was an edge between these two nodes. All right, let's say there was an edge, there was a flight between B and C. Now after having added this flight, if you notice, now each node in the graph is connected. Indirectly or directly, we can move from any city in the graph or any node in the graph to any other city or node. So this is what we called a graph to be connected. This is what we called this is what is called a connected graph, right? So now moving on to what the agenda for today is, which is trees. Let me just write down what a tree is. A tree is a connected graph having no cycles. As simple as that. All right. So if a tree is a connected graph having no cycles, I just ask you this simple question. Let's say a tree has n nodes. A tree has, let's say, n nodes, n number of nodes. What will be the number of edges? Don't write it on the chat. I'll launch a poll. N by 2, n minus 1, 2 into n minus 1. So I'm launching a poll. Just answer on the poll. So 1, 2, 3, 4 basically means ABCD. All right, as expected, all of you guys have answered it very correctly and very fast. Great. So the answer for this is n minus 1. We can simply identify this using an example. Let's draw an example. Let's say we have a node with let's say we have a tree with 5 nodes, for example. So I'll draw a tree. So you can see this is connected. This has no cycles, so it is a tree, and it has 5 nodes. But how many edges does it have? 1, 2, 3, 4. So it is very simple to identify that n minus 1 is the option that was the correct, right? So n minus 1 edges, n nodes, n minus 1 edges. All right. So yeah, now let's look at some different types of trees, different terminologies that are used in trees, so that we can move on and go on to some more interesting and complex part, right? So a tree can be rooted or unrooted. For example, if you notice, once we root the tree with some node, let's say we hold, let's say, imagine this, imagine that the nodes of a tree are beads, the nodes of a tree are beads, and these beads are connected with strings. All right, I hope you understand the analogy I'm trying to say. Let's say if we hold the whole tree, if we hold the whole system with one node, let's say I just hold the bead 1 in my hand, with gravity all of the other nodes will fall down. So this analogy, what I am trying to say is, I have rooted the tree on the node 1. So if there is a root defined for a tree, then the tree is rooted. If there is no root defined for the tree, then it is not rooted. As simple as that. For example, in this case it is my choice. I can say that let's root the tree on 1. So 1 is the root of the tree. Otherwise, the tree is unrooted. As simple as that. So now the tree can be binary tree or a generic tree. So once I root the tree, all right. So if the tree is rooted, what extra things happen? So if the tree is rooted, what happens is we can have a parent-child relationship between the nodes. So initially, what I told was there is a link between some nodes when some nodes are connected by edges. As simple as that. Now once I have rooted the tree, let's say I have rooted the tree on the node 1. So let's call it root. So 2, 3 and 4 are now children of 1, because they come just below 1, and they are connected with 1, right? So this 2 is a child of 1, 3 is a child of 1, 4 is a child of 1, and 5 is a child of 3. And similarly, 1 is a parent of 2, 1 is a parent of 3, 1 is a parent of 4, and 3 is a parent of 5. Note that 4 is not a parent of 5, because there is not any edge between them. So 4 is not a parent of 5, but 3 is a parent of 5. All right. So if you notice, this is a parent-child relationship. So 3 is a parent, 5 is a child. All right. So depending on like once we have rooted the tree, a tree can be binary or generic. By binary, what I mean is, if I no Rishabh, 5 is not a child of 1. If you see, 5 is a grandchild of 1. I was just about to come there. Thank you for pointing it out. I was just about to point it here. Gaurav, it is generic, the second one, GENERIC. All right. Yeah, I'm elaborating the concept, don't worry. So what I was trying to say is, let's say we restrict each node to have maximum 2 kids, maximum 2 children. So it is an example of a binary tree. But otherwise, if there is no such restriction, any node can have any number of children. It is a generic tree. As simple as that. Right? So there is no restriction on number of children. All right. So you answer me this question: is every graph a tree? Don't write it on the chat. Don't write it on the chat. Don't write the answer on the chat. Every graph is a tree. Alright, so 18% of the people have still answered it wrong. I was hoping for a more for a better percentage. Anyhow, so the correct answer for this is false. No, as no, I just told you in the previous slide that a tree is a connected graph having no cycles. So a tree is a connected graph having no cycles. So in this example only, you can see that this particular graph has a cycle. This particular graph has a cycle. So this particular graph is not a tree. So every graph is not a tree. All right. Please give me a thumbs up if you guys understand this. All right, so I'm not getting any confused emojis, so I'm hoping that it is clear. All right, so on the other hand, let me ask you this another question. Every tree is a graph. Is it true or is it false? Answer it on the poll, please. Okay, so the percentage of people giving the correct answer is increased significantly. This time 97% of the people have 96% of the people have answered it correctly, which is nice. So the definition of a tree says, just have a look. The definition of a tree is that says that a tree is a connected graph. So a tree has to be a graph, right? So the in the definition only it says that every tree is a graph. So the answer is true. All right. Oh, it's okay, Brahmajot. Let it go if the option is not coming. I've ended the poll now. All right. So like I said, unrooted, generic, binary, and otherwise it could be weighted or unweighted. Let's say I've given I've given these nodes, I've given these relationships to these nodes via a via edges. So if I give a weight to every edge, let's say this edge has a weight of 5, let's say this edge has a weight of 7, let's say this edge has a weight of, I don't know, -1. Weights could be negative as well. So let's say this edge has a weight of, I don't know, anything, 10. So this becomes a weighted tree. So someone is saying, please give example of an unrooted tree. Rooted or unrooted is in our hands, man. The tree is the same. The relationships between the nodes are the same. If we want, we can decide that, hey, you are the root of the tree. If we do not want, we cannot decide any root. So binary, the specialty of binary tree, like I said, is that it will have maximum 2 children. Every node will have maximum 2 children, and in the generic tree, any node can have any number of children. All right. Cool. So like I said, for weighted tree, if we assign some edges, if we assign some weight to the edges, we can call it a weighted tree. All right. So okay, so someone is asking, so what is its significance? Why do we add weights to the tree? Imagine that we have a network of cities, and between each we have a network of cities, and and a train system. Let's say we have distance between each of the two cities. So the distance can act as distance can act as the weight of the edges to signify how far these two nodes are. Regarding negative weights, let's say it is profit or loss. Let's say if you move from 1 to 4, you have to give 1 rupee to go there. Let's say if you want to go from 1 to 2, you are given 5 rupees. I'm just giving a very lame example. I can't think of a very good example as of now. Yeah, so let's move on. We have spent enough time on this. So like I said, these are the types of trees that can be there, and apart from that, in case of a generic tree, I defined what a root is. This is a root. So now once we have rooted the tree, like I said, I also defined that for this is a parent and this is a child, right? So now once the tree is rooted, every tree every node has a level associated with it. So the level of 0, level of the node 1 is 0, the level of the node 2 3 4 is 1, the level of the nodes 5 and 6 is 2, right? So we can associate a level with each node, because as it is very clear, as we can see it very clearly, just the direct children of one can said to be have a level 1. The children of level the children of node 1 can said to be have a level 2, and so on and so forth. All right. So a tree has a height as well. So for this case, for this binary tree case, if you see, the height of the tree is 4, because 1 2 3 4, right? Although it is in one manner we can see that the height is 2 also, but I'm talking about the maximum height. So the height of the tree is 4 in this case. So, and the height of the tree is 3 in this case, right? So yeah. And another thing that another set of definitions is ancestor and descendant. All right. So someone is saying, is height equal to max level? You can say that height is equal to max level plus 1. It depends on us. If we label the levels starting from 0, if we label the levels as 0 1 2, then it is max level plus 1. Otherwise if you label it 1 2 3, then it is equal to max level. All right. So like I said, about ancestors and descendants. So if you notice, once the tree is rooted, let me just give you a bigger example. So once the tree is rooted, if you notice, every node has some nodes contained in itself. For example, this particular node 4 has the node 5 6 7 and 8 under itself, right? Now note that this 5 is not under this 3. This 5 is under this 4, but this 5 is not under 3, right? So this part of the tree is called the subtree of 4, because this node 4 contains this particular tree under itself, right? So here we introduce the concept of subtree, and all of those people who are asking me the use of all these things, and like Dharya is saying, where do we need to specify? Give me 5-7 more minutes. Once I am done with the definition part, I'll just give you an example. Yes, the subtree will include 4 also. All right. So yes, so this is the subtree. So for ancestor and descendant, since 5 lies in the subtree of 4, 5 is a descendant of 4. Since 8 lies under in the subtree of 4, 8 is a descendant of 4. Now since 8 lies in the subtree of 4, 4 is an ancestor of 8. So basically, if I am to talk about 8 and 4 in this particular example, 4 is an ancestor of 8, and 8 is a descendant of 4. All right. Cool. So someone is asking, will the PPT or notes will be shared? So whatever I am writing, I can share that on Discord. Don't worry, I'll share this. All right. So yeah, I hope the ancestor and descendant part is clear. Now another thing that I want to sort of discuss with you guys is, in a tree, let's say I am asked, like the provision is that we can move from one node to another, using these edges only. So for example, if I am to move from 2 to 4, so 2 to 4, so I had to traverse through 2 edges. So we can say that the shortest distance between 2 and 4 is 2. All right. Let's say I am asked that you have to move from 5 to 8. So if I am to move from 5 to 8, what I can do is go to 4, then go to 6, then go to 8. So the distance between 5 and 8 is 3, right? So similarly, between 7 and 2, if I am to give 7 to 6 to 4 to 1 to 2. So the distance here is 4. As simple as that. Yes, Meghna, you will be able to access the videos after the session. All right. So if we like through the examples that I just show you, isn't it clear that there will be unique path from one node to another node in tree? We can see, right? We can observe that here. Like I could prove that also, but that will probably take a lot of time. So I'll let it go for now. So you can you observe it from there only, from here only. So unique shortest paths, unique shortest paths. All right. So now let's notice. So what we are doing is, from when we are going from a particular node to particular node, we are going in some upward directions, like some steps in upward directions, then coming back down. So for example, if I was to go from 5 to 8, I'll be going one step up, which is to 4, then coming down, right? So this 4 is what we called in LCA of 5 and 8. So because when I was to go from 5 to 8, I went up till 4, then I went down and down and down till 8, right? So what we call is that. Also, since many, yeah, I'll tell you what LC means. Many people are asking, this is one an ancestor of 8 and so on and so forth. So a node can have multiple ancestors. So for this 8, 4 is 6 is also an ancestor of 8, 4 is also an ancestor of 8, 1 is also an ancestor of 8, right? Because 8 lies in the subtree of 6 as well, 8 lies in the subtree of 4 as well, 8 lies in the subtree of 1 as well, right? So like now coming back to going from 5 to 8. So like I said, if I am to go from 5 to 8 from or any other pair of nodes, I am Piyush, I am reading doubts here, not at Discord. So when I am to go from 5 to 8, I'll just go up until 4, then keep coming down. So like I said, this 4 is called LCA of the node that I go up till and then come down. It is the lowest common ancestor of 5 and 8. If you see, 1 is also ancestor of both 5 and 8, but 4 is also ancestor of both 5 and 8. So since 1 has a level higher than, since 4 has the a level lower than 1, so that is why it is called lowest common ancestor of 5 and 8. So I'll just ask you a simple question to get an idea about whether is it clear or not. Just tell me, what is the LCA of let's say 2 and 7. So is it 2, is it 1, is it 3, is it 4? So I am launching a poll. All right, so most of the people have answered it correctly, but still some of the people are not being able to answer it correctly. So the answer is 1. Again, just see now, let's say we are at 2 and we are at 7. So look at all the ancestors of 1, look at all the ancestors of 2. So 2 is an ancestor of itself because 2 lies in the subtree of 2, but 2 is not an ancestor of 2. The 2 is not an ancestor of 7, so 2 is not the answer. Then go up, 1 is the ancestor of 2, right? Then see, yes, 1 is ancestor of 7 as well. So 1 is the lowest common ancestor of 2 and 7. So I'll just write as well. LCA basically means lowest common ancestor. All right, great. So yeah, let's move on to different types of let's move to different ways to represent a tree. All right, so how can we represent a tree? Like I said, what is a tree? It is a set of nodes. Let's say we have n nodes, and each of the node is numbered from, like, the nodes are numbered from, let's say, 1 to n. As simple as that. So now, as we know that each node, there will be n minus 1 edges, right? So what we can do is, one way to store it is that just store the number of nodes, which is n, so that we know that the nodes are from 1 to n. and just store the list of edges. So it can be stored as a list of edges. Another way to store is that another way to store is an adjacency matrix. Adjacency matrix. So for adjacency matrix, what we can have is, let's have a n cross n matrix, and n cross n boolean matrix. So basically 0 means that there is no edge between I and j, and 1 means that there is an edge between I and j. So let's say there is an edge between 1 and 2, so I'll do 1 here. Let's say there is an edge between 1 and 3, so I'll do 1 here as well. So let's say there is no edge between 2 and 3, so 0. So there's an edge between, let's say, 1 and 4, so 1. Let's say there are no other edges. So this particular adjacency matrix will represent this tree. So there's an edge between 1 and 2, there is an edge between 1 and 3, and there is an edge between 1 and 4. So this is one of the ways you can store the tree, but it will take of n square space, right? So if there are n nodes, it would take of n square space, but it won't but we don't require this much of a space, because generally in the constraints it is given that n is less than or equal to 10 raised to power 5, and we cannot afford this much space. So Aryan is saying, can you repeat edge part? All I'm saying is that if matrix of ij equals to 1, it means that there is an edge between them. If matrix of ij is 0, it means that there is not an edge between them, right? So let's just quickly look at some other methods. Another method could be storing the parent of each node. If you notice, if the tree is a rooted node, so every node has a unique parent, right? 2 has its parent as 1, 3 has its parent as 1, 4's parent is 1 in this case, 5's parent is 4, 6 parent is 4, and so on and so forth. So what we can do is we can store parent of each node, right? So this is one way to go about it. Another way to go about it is, which is generally preferred and which is generally required, is, I'll just go forward from there only, is storing an adjacency list. So what we can have is we can have a list of n nodes. So and in each of these indices we can store that what all edges this node has. So for example, if I'm to talk about this tree, 1 has edges with 2, 3 and 4. So in the index 1 we can store 2, 3 and 4, right? So we can store at the index 1, 2, 3 and 4. So now coming back to 2 has an edge with 1 only, so in here we can store 1 only. So then going back to 3 has an edge with only 1, right? And then in 3 we can store 1 only. Then for 4 we have edge with 1, 5 and 6, right? So store 1, 5 and 6 here. Similarly for 5, let me just complete it very fast. 5 has an edge with 4, so 4 here. And then 6 and 7 also we have. So for 6, if I see, 6 has an edge with 4, 7 and 8. So 4, 7 and 8. And 7 had an edge with 6 only, 8 also had an edge with 6 only. So we can store the edges in this manner as well. We don't really need map of list. What we can have is vector of vector int, vector of vector int adj of size n plus 1. Why n plus 1? Because my indexing is 1 to n only, so that is why I am taking n plus 1 instead of n. All right. So yeah, there are trade-offs between each of the method. Like if we are storing parent array, we can we can get the parent in O of 1. If we are storing adjacency list manner, we can get to know what all nodes are my neighbors in a very efficient manner in the adjacency list, right? And if we are storing adjacency matrix, For a pair of nodes, we can get to know in order of 1 that whether this pair of nodes have an edge between them or not. So every way has its pros and cons. All right. So yeah, so what to use will depend on the type of question that you are trying to solve. I hope you understand this. So now what we'll be doing is we'll be looking at a way to traverse the tree, to sort of to sort of traverse the tree. All right. So by traversing, what I mean is visiting all of the nodes of the tree once in some manner. One way to traverse the tree is something which is called depth first search. Depth first search. So let's say we have this tree only. Let's say what we have this tree only. So what we will be doing is we will be writing a recursive function in which first we will visit this node 1, and then we would go to 2, because 1 is because 2 comes before 2 is a 2 is a child of 2 is a child of 1, then to another child of 1 which is 3, then to another child of 1 which is 4, then to one of the children of 4 which is 5. Let's say we had this 8 as well. So then after having visited 5, let's say this is 9, so we would go to the child of 5 which is 9, and then come back, then 4, then another child of 4 which is pending 6, then again one of the children of 6 which is 7, and then to 8. So if you notice, we are going in the depth. So once when we were at 1, we went depth wise in this subtree. So since this subtree has been exhausted, now this 2 subtree has been exhausted, now we are going to 3. Then now again the 3 subtree, the subtree of C3 has exhausted, then we are going to 4. Then now we will again try to exhaust the subtree of 4. So pick up one of the children of 4. Now first we will exhaust the subtree of 5, then go to any of its other nodes, then go to any of its other children. So yeah, coming to 5, then going to its subtree more deeper to 9. So now the subtree has been exhausted. Now then go back, then to another node which is 6, then exhaust one of the subtrees, and then go back, then another subtrees, right? All right. So this is a possible depth first search that I proposed. Now going left to right or going right to left, like we are exhausting which subtree first will depend on how the adjacency list has been stored. All right. So let's say in the adjacency list of 1, we had 4 first and 3 afterwards. Then we would be exhausting the subtree of 4 first and then the subtree of 3. But otherwise, if we had 3 stored in the adjacency list of 1 before 4, so then we would have been exhausting the subtree of 3 before the subtree of 4. So which subtree is being exhausted first depends on the adjacency list. All right. So Neil is asking, are you going to write a program for DFS using vector vector? Yes, Neil, that is what I'm going to do now. So now what we will be doing is, just to give you an idea, we will be writing the code for depth first search. Before that, what we'll be doing is we will be using the adjacency list to take input of a tree to store the tree. Then we will be iterating, when we will apply depth first search on that particular on that particular tree, and then we will try to find the level of each node. All right, the level of each node, and we will try to find the number of nodes in the subtree of each node. All right, exhausting, by exhausting I meant visiting all of the nodes in that subtree. So Stephen Raj was asking, what did I mean by exhausting? By exhausting I meant visiting each of the node from that subtree. So for homework problems, I think they have been added to the practice contest. You can have a look at a couple of problems from there. All right. So let me just share my screen with you guys now, and we'll just get down to the coding part. Give me a minute. What I'll do is I'll just open the Unacademy app on my phone so that I can have a look at your comment section. At the comment section. Just a moment. Yeah, so I have opened it. All right, great. So regarding this setup, please ignore this. What I'll just tell you briefly what it is. It is just to make my life a little bit easier. So in vector we have this function called pushback. We have different functions, make tuple, make tuple, make pair, and so on and so forth. So I have just been using short forms for that so that I can save a couple of seconds when I'm writing the code. So regarding sharing this template, all right, sure, I'll share the template with you right now. So I'll just give me a second. I'll just paste. All right, so I'm writing it. I'm commenting down the pastebin link. You can get my template from there. All right, so let's get down to the problem solving part now. Great. Be alert now, and like I said initially, what we'll be having is we'll get as input the number of nodes in the tree. So int n, scene n. Then we know that the number of edges in the tree are going to be n minus 1. So what I'll be doing is for int id equal to for int, let's say I'll be iterating n minus 1 times, right? I have to take input of all the edges. All right, so once I'm taking the input of all the edges, what I would need is an adjacency list. So for that, let's say we have this adjacency list, and I'll also sort of define them globally so that I don't have to pass it to the DFS function separately. So I have this adjacency list, I have this n globally. So as soon as I take input of this n, what I would do is I'll just resize my adjacency list to n plus 1. All right, so c in n adj dot resize n plus 1, and then let's say we are getting the input of edges, and int u v c in u v. Now we know that we will have to add v to the adjacency list of u and u to the adjacency list of v. So I am just doing what is required. So adj u dot pushback v, adj v dot pushback u, as simple as that. So after having taken the input, like I said, let's say we decide, let's say it is given in the question. So generally it will be given in the question that assume the root to be 1. All right, so let's say the root is 1. All right, root is 1. So now if you notice, what I am to do is in here itself, let me explain first, then I'll code. So let's say we have this. Let's say we have this, and let's say there are also a lot of big subtrees in under these nodes. All right, I am just not drawing them. All right, so what I'll be doing is we will start from the root. All right, we will start from the root. So the first node that we will be visiting is the root. Utkarsh, why n minus 1? It has been discussed that in a tree we have n minus 1 nodes. All right, so 2 3. So what we will be doing is we will be calling we will be making a recursive call to 2. So a recursive call will be made to 2 3 and 4. All right, so what we will be doing is we will be making recursive calls to each of the children of the current node for the DFS function, and before that I'll just print the current node. All right, so now I know that 1 one is 2, 3 and 4 are the children of children of 1, and now let's say we have this these node 5 under 2. So when I'm at 2, I'll have to make a recursive call at 5. So now the problem here will be, in the adjacency list of 2, I don't know whether the current node is parent or child. So but we know that only one of the nodes is going to be parent. So we know that in the adjacency list of 2, we will have 1 and 5. So let's take an example of this node only. So okay, let's just let's just make a adjacency list of this. So 1, 2, 3, 4 and 5. So I know that in the adjacency list of 2, I will have 1 and 5, right? So now when I am to make a recursive call to 5, I need to somehow keep track that hey, 1 is my parent. So since 1 is my parent, I don't have to make a recursive call to 1 again, because that will end up in an infinite loop. So to make so for doing the DFS in an efficient manner, in a correct manner, what we would need is, in the DFS function, I will need that what is the node that I'm currently at, right? So for DFS, what we will need is, we will need the node that I'm currently at, and I would need to store what my parent is. All right, so why is this parent needed? This parent is needed because when I'll be iterating over the adjacency list of the current node, I need to know that hey, this node is my parent, this node is my child. So since there is only one parent, instead of storing all the children, I am just storing parent here. All right, so initially, like I said, we have to start the DFS from the root. I'll just give a default value to the current node, which is 1. So since there is no parent of the root, so in this particular case, in a rooted tree, we know that the root will not be having any parent, so we can just give any value to the parent, any invalid value to the parent. Let's say I give -1. All right, so when I am at any node, what I'll be doing is just print that particular node, and then is my screen not visible? I think the screen is visible, man. I'm sorry, please try refreshing, Siddharth. So I'll be printing the current node. Then I need to call recursive, I need to make a recursive call to all of my children. So what I'll be doing is, I am just iterating over its neighbors in the adjacency list of current. So this neighbor can be parent or it can be child. So what I'll be doing is, if the neighbor equals parent, so if the neighbor is equal to my parent, I know that I don't have to make a recursive call now. So in this case, I'll just continue. So if the neighbor is not equal to the parent, now I know that hey, this particular node is my child. So then I'll just make a recursive call to the neighbor. Now the current node will become equal to the neighbor. In the recursive call, the neighbor will be treated as current. Now what is the parent of this neighbor? Since this neighbor is child of myself, it means that I am the parent of that node. So here I'll be passing current. All right, so this is how it will go, and let's try it for an example. Let's say let me just draw a tree, and then I'll give an input. Let's say we have this tree. All right, so let's just try. So the number of nodes are 7, and what are the edges? 1 to 2, 2 to 3, 3 to 4, 4 to 5, 1 to 6, and 6 to 7. Please correct me if there is anything wrong. 1 to 2, 2 to 3. Okay, this is not 3 to 4, it should be 2 to 4. All right, so 2 to 4, and then 4 to 5, 1 to 6, and 6 to 7. It seems to be the correct one. So let's just run the code. All right, so let's see what the order is. The order of the DFS, what it should be 1, which is right. then going to one of the subtrees 2, which is right, then picking out another subtree and going there, which is 3, which is right. 1 2 3, the order is right. Then picking out another subtree, which is 4, right, then going towards the depth 5, which is right, so 4 5. Then this subtree has been exhausted. Now going to another subtree of 1, which is 6, right, then 7, right. Got it? So this is how a very simple DFS would look like. All right, so yeah, so now let's just see how can we calculate some things like level of each node and level of let's just find the level of each node. All right, so now if you notice the level of each node, can we say that the level of each node will be equal to the level of my parent plus 1? Give me a thumbs up if you understand this part. So level for every node will be equal to the level of its parent plus 1. All right, great, cool. So let's have two another vectors. Let's say level and another one, let's say subtree size. All right, I'll just also resize them as well. So level dot resize n plus 1 and subtree size dot resize n plus 1. As simple as that. So I am printing the nodes, which is fine. Let's say I'll just not print the nodes. Let's say what I do is I just say level of current equals to, okay, just a second. So let's just say level of current equal to level of parent plus 1. And after having called the DFS function, I print all the levels of the nodes. So let's say I print I and level of I. I'm not writing it right now. I'm not running it right now. Let me just draw the tree first. Let me just draw it here so that we can have it with us every time. So 1 2, just have a close look at the code. I want you to find the mistake in this code. Is this code correct or is this wrong? Don't answer that. I'll ask you guys on the poll. So 1 to 2, 2 to 3, and 2 to 4, and then it was 4 to 5, I think, and then it was 6 and 7, right? This was the tree, right? All right, so let's see. Rn is saying, won't the parent be -1 in current equals 1? Yes, exactly. That's one of the problems that is there with the code. Very good. So instead of this -1, what we can do is we can have the parent as 0. So the default value of the levels is 0 only. So what we can do here is, before passing on the before calling the DFS function, I can set the level of 0 equals to -1. So now the level of 1 will be set to 0, which is what we want. All right, but there is another mistake. Let me give you a hint. The other mistake is with the line number where I am setting the parent, where I am setting the current. Arjun, it should be outside the for loop only, na? Yes, Aryan, you are the answer is correct. Kshitij, you are also saying yes. The people who are answering are answering correctly. Okay, so let me just explain to you why is it wrong. So what I am saying is level of current equals to level of parent plus 1. So if you notice, I am starting my DFS calls. I'm starting my DFS call from 1, right? So then I am when I'm going in this for loop, right? In this for loop, and then calling DFS of 2, right? And then again I am going into this for loop, then calling DFS of 3. Now the problem here is, when I have come to 3, I have not even set the levels of 2 and 1 as of now, because recursive call is being made before setting the level. So since when I am calling the recursive call for my child, my level should have been set, right? Because my child's level is dependent on my level. So but the recursive call has been made before setting my level. I hope this makes sense. Please give me a thumbs up if you are understanding what I am trying to convey here. All right, so I have some thumb confused as well, but I think most of the people have understood. So I'll just repeat again. So this is now correct, this is now correct. That was wrong because I was setting the level of the current node after having done the recursive call from my children. So when I'll be doing the recursive call for my children, they won't be getting the original level of my, they won't be getting my original level, which will give us the wrong answer. So if I am to do this, what you will find out is that the level of each node will be wrong. Let me just print it. So you can see that level of 1 is 0 and all other levels are given as 1, which is wrong, which is clearly wrong. But if I do it like this, then it will give us the correct answers. So yeah, now you can see that the answers are correct. 1 has a level 0, 2 has a level 1, 2 and 6 has a level 1, 3, 4 and 5, 3, 4 and 5, 3, 4 and 7, sorry, 3, 4 and 7 have levels levels 2, and 5 should have a level 3. Okay, so Aman, to answer your question, to be very honest, we don't really need to initialize the values of level. Why? Because we are just initializing it here now, and we have initialized the level of 0 here. But even after that, let me just tell you that that the default value set in vector is 0. So it is initialized by 0. All right. All right. So some people are saying, what is the difference if we set the level for if we set the level inside the for loop? Okay, so inside the for loop, what you are suggesting is before this DFS call, is that what you are suggesting? Is that what you are suggesting? Level of neighbor equal to level of current plus 1. So this also works without any problem. Why? Because we know the level of current now, and before actually making the recursive call, we are setting the level of neighbor, which is also fine. So you can do it like this as well, or you can do it like how I told. All right, great. So I think we don't have any time left for the problems now. I'll just discuss one more thing with you, and we'll just call it a day for now. I hope you have gotten a very good introduction to trees as of now, and now what I am trying to do is I'll be calculating the subtree size for each node. For example, if you notice, for this tree, the subtree size of 5 is 1. Subtree size of 4 is 2. For 3 it is 1. For this 2, this is 4, and for 7 it is 1. For 6 it is 2, and for 1 it is 7, right? So I'll be trying to calculate the subtree sizes of each node. All right. So now if you notice, how can we calculate the subtree size for each node? Someone was asking me to scroll down. I have scrolled down. So to calculate the subtree size of each node, can you notice that can you notice that for a particular node, subtree of I will be equal to summation of u belonging to children of I, subtree of u plus 1. So if you notice, what we can say is, let's say I want to calculate the subtree size of 1. So if I want to calculate the subtree size of 1, I know that it consists of these two parts. The one part is which is the subtree of 2, the another part is which is the subtree of 6. So if I have if I have the subtree size of 2 and I have the subtree size of 6, what I can do is just add both them up, add subtree size of 2 and subtree size of 2 sorry, subtree size of 2 and subtree size of 6, and then add 1 to it, because one of the nodes is the current node itself. All right, so subtree size of a particular node can be calculated as the sum of subtree sizes of all its children and then adding 1 to it. All right, so someone is asking me to share this code. Yes, I'll just share this code in the Discord channel, don't worry about that. All right, so now again we have the subtree sizes. Now let me know what, let's say I initialize the subtree size of current equal to 1, right? Let me just comment it out now. So like I said, the subtree size will be 1 plus the summation of children. Now let's say what I do is subtree size of current plus equal to subtree size of neighbor. Now tell me, is it correct or wrong? Is it correct or wrong? Yes, people who are asking, the people who are answering is correct. So here as well, if you see, I am adding the subtree size of neighbor to myself before actually calculating the subtree size of the neighbor. So when will the subtree size of neighbor be calculated? When I'll make this DFS call. So but before making this DFS call only, I am updating the size of subtree, which is not correct. So what will be done in this case is that after the DFS call, we'll update the subtree size of the current node. Now for people who are saying that it is a bit confusing and all, I'll just give you a thumb rule. So what's happening here is, like you saw that we are using DFS to calculate two different values here. First we use DFS to calculate the level, then we use DFS to calculate the subtree size for each node. Now the placement of the updating part, like the placement of where to update the values, will depend on one simple fact. The fact is that whether the value of the node depends on its parent, or does it depend on their children. So if it depends on their children, right, if it depends on their children, you will need to update the value of the current node after having made the DFS calls, because only after having the DFS calls, only after having made the DFS calls, you'll be able to get their values. But if the value of the current node is dependent on its parent, so in that case you'll have to update the value of current before having made the DFS calls, because my child's value is going to depend on my value. So yeah, I'll just update and show you guys. So subtree size I am printing now. So yeah, you can see subtree of 1 has just a second, let me replace this by tab character. So yeah, subtree of 1 is 7, 2 is 4, 3 is 1, 4 is 2, 5 is 1, 6 is 2, 7 is 1, which is correct. All right. So yeah, I hope that what we have learned today makes sense to you guys. Are you guys with me? So yeah, I was hoping that we may be able to discuss one question as well, but I'm sorry about that. We have not been able to discuss that question. But I can tell you that that the questions that one of the questions that I was able to discuss was this. You can search this on Google, FamTree CodeChef. All right. So you can search it. Otherwise, it is also on the question is also there on the on the contest page. I'll also update the code that I just wrote on the Discord channel. You can have a look there as well. So I'll give the link to the problems in the Discord channel. Don't worry, you'll get it. You'll also get the code. I'll also update the code on the Discord channel as well. All right. And regarding all of your queries regarding whether the recording will be available or not. Yes, the recording will be available after the session. It will be available on Discord. Sorry, it will be available on Unacademy as well as YouTube. All right. So recording the Discord link. Aman, can you please share the Discord link if you are here? All right. So Aman will be sharing the Discord link. I am waiting for him to share the link. In the meantime, let me just revise what we have done today. All right. So we discussed in brief what a graph is. Then we very quickly moved on to what a tree is in terms of graph, right? A tree is a connected graph with no cycles, all right? Then we discussed various terminologies and types of trees: rooted, unrooted, binary, generic, weighted, unweighted, and so on and so forth. And so people who are asking me for the Discord link, Discord channel, this is the channel. All right. So so uh, uh, so so the other things that we discussed were that they have unique shortest paths, what is LCA, different ways to represent trees, adjacency matrix, adjacency list, parent array, and so on and so forth. And then we discussed DFS. So we discussed DFS, and we did not use any visited array in that. That's something that you should have noticed. If you guys already know about graphs, in graphs, whenever we do DFS, we have to we have to have a visited array to keep track of what all nodes do we have visited and what all nodes we have not visited. But in the tree, we did not need any visited array, because when we are at a particular index, when we are at a particular node, we know that its neighbor has been visited, but none of its children has been. All right. So then we updated the code to find two different things: what are the levels of each node, and what are the subtree sizes of each node. And then we discussed sort of and learned about the importance of the line number where the values are being updated. All right. So that's a very important thing that I should sort of recommend you to take with you. All right. So some people are asking me about the contest link. I'm sorry, I don't know what the contest link is. I was being told that there is going to be a practice contest. Most likely you'll get the link. If there is any contest link, you'll get the link in the Discord server only. I'll just try to figure out if there is any link, and if the link is there, I'll just upload it on the Discord server. On Discord server, Rahul, and the link to the Discord server is there in the Unacademy chat. I have pinned that particular comment. So yeah, it was very nice having this session. I hope you guys enjoyed it. And I'll be also, yeah, I'll share the code. I'll share the code immediately just after ending the class. I'll put it in the Discord channel. And I'm having another session. I don't know if you guys would like to have that session, to attend that session or not, since it is a Div 3 session on basics of maths at 8 p.m. So some more basic stuff will be covered there. If you want to, you can join that as well at 8 p.m. All right. So yeah, maybe see you guys on Sunday then. On Sunday we are having another session on BFNs and DFS spanning trees, which will be covering some questions as well, because that session is going to be 2 hours long and we'll have some more time. All right. So okay guys, it was great having this session with you guys. I hope you guys enjoyed. Thank you very much. I'll be ending the class now. All the best for your rest of your classes, and I'm sorry to have taken 10 more minutes of your time and extending the class. All right, bye now.